Welcome everyone to the workshop Highly Integrated Battery Thermal Management System of the MARBLE project. Just a quick look to the agenda. We have a slight change in the agenda as we have no local or no personal meeting, no personal workshop, as most of the attendees registered online. We eliminated the coffee break, so whenever you are going for coffee and you might miss some bits and pieces, the whole workshop will be recorded and you get a link to the recorded workshop, and so you can check for whatever you missed afterwards. First, the welcome and introduction. Those three people are currently showing their faces in the workshop. The first one, I will start with the introduction. My name is Christian Hannemann. I'm with the Fraunhofer IWU, the Institute for Machine Tools and Forming Technology in Chemnitz. I'm working in the Department of Functional Lightweight Design already for 18 years, strongly involved in metal forms and other lightweight structures. And I'm in the project MARBLE engaged in the thermal management as well as in dissemination and exploitation. Usually my expertise is in casting, extrusion, and foaming of aluminum. And we work a lot in recycling processes, integration and transfer. So I now hand over to Sandor, who is the second on the picture.
Yeah, hello everyone. My name is Sandor Eichinger. I'm the technical lead at AVL Deutschland GmbH, AVL Germany. I'm responsible for 3D simulations in battery, including thermoelectrical simulations, as well as thermal propagation simulations. And I'm also, responsible in the MARBLE project for the development of the thermal management system. So, that's maybe enough.
Valerio, it's your turn.
Hello, everyone. My name is Valerius Boxberger. I'm with AVL for more than 8 years. Most of the time I was a team leader for battery simulation. Right now I took over the position as a project manager for research and development, managing and coordinating a lot of research topics, national and international. And I'm really happy to have you here, and hopefully we will show you some interesting technical solutions. Okay, Christian, let's start.
Yeah, so we're heading off to the first presentation. It's about the next generation cooling solutions, meeting today's and tomorrow's challenges in battery and electronics cooling. Just to give you a short impression about what we are going to see. First of all, we talk about a little bit about the project itself, about MARBLE, the consortium challenges, some objectives and impact, then some actual achievements, so all the achievements we have done so far, the next events, and some special challenges that appeared during the project period. So starting with an overview about MARBLE, I hope that is working. We've got a small video, and so that you don't.
The transport sector is the largest contributor to the EU greenhouse gas emissions, being road transport accountable for over 70%. According to the European Environmental Agency, passenger vehicles can emit up to 182 grams of CO2 per occupant in a kilometre, which can be cut to just 30 grams with the adoption of electric vehicles. To reduce transport emissions in line with the European Union's climate neutrality objectives, the MARBLE project is designing and developing innovative and competitive batteries with a reduced charging time by 25%. And a lifespan of 300,000 kilometers, almost doubling the life of current batteries. The battery pack being developed includes an advanced battery management system, power electronic components, A thermal system to maintain cells at their ideal working temperature through a water-cooled battery, and an ultra-fast charging solution. The batteries have an innovative design, the presence of recycled materials, and include circular economy approaches, ensuring that they are easy to dismantle, refurbish and repurpose for second life applications. All to reduce batteries' environmental impact and vehicle weight up to 20%. Marbel, towards an environment-friendly and lightweight mobility. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme.
Right. So you have seen already some bits and pieces about our project. Just a short introduction of the consortium. The Marbel project contains 16 partners from 7 European countries. We have 16 research centers involved, 5 tier 1 and 2 suppliers, and ABL is one of them. Who is presenting today. We have 1 battery recycling company, 2 SMEs, 1 automotive engineering supplier, and 1 OEM, which is Stellantis. The project had a duration of 4.5 years, ending on the end of this month. Was led by Eurecat and had an overall budget of about 12 million euro. Yeah, it was funded by the Horizon 2020 EU funding. And what are the challenges of this project? What we have to do is accelerate the mass market of the BEV, and I would say all the electric vehicles, get a more sustainable and efficient vehicle, and contribute to the EU policies meeting the emission targets of 55% by 2030. And how is that done? Of course, we increase the energy density, reduce the weight of the whole structure of the whole battery pack, optimize the battery system's performance, extend the range we are allowed to travel, and decrease the charging time, as no one wants to stay on a petrol station very long or on a charging station very long. We increase the battery lifespan and reduce time and costs as well for manufacturing as for maintenance. And there is a repurpose of second life application. So we're going to use it in other applications like scooters or whatever, and reduce the environmental impact. Everything you see is compared to the Audi e-tron, which is registered here as well. So how are the objectives and impact? We have 3 big areas in that. The first one is the design for circularity. So we are using modular and lightweight design, recycled alloys to create, for instance, the battery boxes. I come to that later on again. Weltless modules, also a point I will explain in a future presentation, and wireless communication. Then we have the performance improvement, containing the thermal management improving, ultra-fast charging, a new type of BMS, and wireless communication. And last but not least, testing and validation and dismantling. We have test procedures which contain AI as well, and a validation in the evil. It sounds evil, but it's meant to be the electric vehicle in the loop, a testing platform I explain later on as well. And we take care for safe dismantling. Altogether, our intention is to reduce the weight for about more than 20%, have a battery lifetime that you heard already in the video of about 300,000 kilometers. Try to reduce the charging time for a quarter, so 25%, have an LCA improvement of more than 40%, and reduce time and costs for assembly, maintenance, and testing. And it's all designed for easy and safe assembly and disassembly. It's supposed to be repairable and allows a second life transition, and is adaptable. It is supposed to be adaptable for different cells and vehicles. So we are not connected to a certain OEM or car. The first point, I explained it already, of those three is the achievement in lightweight design as a sustainable housings. Yeah, you see we are using recycled aluminum alloys. I'll come to that later on again. Optimized aluminum extruded profiles I will show, and a modular design. So it's scalable. You can use it for smaller battery sizes and larger ones. We have in this modular design a safe and easy disassembly and assembly. Most of those solutions are used like screwing instead of welding or gluing. We haven't got a welded bus bar, it's a screwed bus bar I will show later on, or we will show later on, and it's flexible as well. So for easy dismantling, easy to handle. And the methodology for eco-design, so the approach has a unified approach for LCA and LCC, and the circular economy. And it's focusing on the hotspots, involving not only the development, it's also involving all stakeholders from the beginning, so from the design phase, manufacturing, use, and end of life. And of course, there are implemented eco-design strategies as well. So coming to this second box I showed in the beginning, some achievements have been done in ultra-fast charging strategies and enhanced thermal management. The thermal management is a special lecture I show we show during the whole presentation. So the ultra-fast charging control algorithm is a new one implemented. We take care for charging station preparing of high power. So we have a battery switching between 400 and 800 volts. So we have demonstrators on both, ensuring the proper energy is coming into our battery pack. Then the enhanced thermal management will be shown in the next presentations. So it's supposed to be an efficient cooling panel on top and bottom. And you will see it that we use functional aluminum profiles for that, which have a mechanical job and include functionality of thermal management as well. Also, we investigated some application of aluminum foam. In this case, I will explain why the foam in the end didn't appear in the final demonstrator, but that's also in a future presentation. And in the battery management system, which is, I would say, the foundation for a second life application, we have flexible and modular BMS to adapt to a large variety, so we are not connected to one certain car or one OEM. And it's meant to be also for other applications, contain a small cell manager and wireless communication. So that reduces the wiring and this way, again, the weight. And have an AI-based expert system providing predictive early failure detection. So it's there are sensors included in the system, and those sensors and the data transmit to the cloud with a secure communication channel. So we have a complex functionality included. And the third of those bubbles I've shown before is the testing, validation, and dismantling. So we are using, as I said, the EVIL, which is the electric vehicle in the loop. So it's a flexible and versatile test bench that can be adapted to almost every car you can think of. And it eliminates the necessity of constraints, which are usually given by certain cars, and opens up the potential for almost every application. There's a reduced time consumption and costs for the testing, as you don't have to adapt it to a certain frame and then have to transport it or transfer it to other systems. You can use it, I would say, in one platform for all of them, and the demonstration of the complete pack is available as well. And in the testing, we have procedures for the characterization and validation of the performance and safety. So we optimize the end-of-life tests for the inspection of a second life, and sorry. The AI data processing reduces necessary tests, so it saves about 20% of time for those testing. And mechanical test procedures are done on a miniaturized housing. And as I said, the dismantling, we increase the safety during dismantling of packs without energy needed for like sawing, mechanical cutting, laser, or others. Yeah, that was I would say the biggest steps that were the biggest steps of the project. So in the beginning, we set up the requirements. So that was done for the safety, modularity, for second use, performance, and eco-design. Second step was the development of the solutions and components. In the third step, we had battery manufacturing, assembly, and disassembly. And last but not least was the validation and demonstration. So we are, the arrow shows it, right on the end of the project. As I said, on the end of this month, the project will finally end. Yeah, and talking about the end of the project, you see that or there will be a final event next week. So feel very invited to join. On the one hand, it's possible to join directly in person in Torino in Italy. And on the other hand, of course, as usual today, we have a hybrid format. You can join online as well. It happens next week on the 19th of March from 8:30 to 17:15. It will be done at the Center Research in Fiat in Torino. And the online streaming is available as well if you register, I would say, on LinkedIn or whatever posting you received in the last days. I talked about special challenges in the agenda. We had some special issues in the beginning that were a bit of a challenge, and we overcame these obstacles quite fast, which was very nice, and a good teamwork in the project. The first one was that we ordered some cells from CATL. Those cells had no connectors on there, or had connectors on there, and then we ordered the next batch and they had no connectors. So we had to find a certain solution how to connect those cells to the system. We started with the designing phase and everything else, ordered the next cells, and then there was an issue with this order, and we had to change the whole case of design as we had to change the cell. So we switched to CALB cells. There's some definition of the cells shown here. Those cells were used, had a different dimension, so all the design work had to be done again and adapted to the new design. And this way, some of the approaches we had, for instance, for thermal management, switched in this moment. And that was a place when one of the technologies I was responsible for, the metal foam, was actually eliminated in the system because there was no space for it anymore. Yeah, I will show that later on, but you see on the right side already some different approaches. The first one was a cooling panel underneath the battery cells, and even in between those cells, there were cooling panels placed in the original file. And later on, with the new cells, there was not enough space for that, so we had to find other solutions. So we had a change of the design and switched to alternative solution. A new challenge, but we overcame those obstacles as well. Yeah, what do we need all those approaches for? The problem at the moment in electromobility and also in other electric systems is that the electrical power of those systems, the density of this power is increasing. So we get more and more hotspots in the systems, and we have always limited space. So we need new cooling solutions, as those cooling solutions actually limit what is possible to achieve, and therefore limiting in the electromobility the maximum range and charging speed. And some of those further investigations will be shown in the next lectures. and also the combination of 4 EU-funded projects will be very shortly mentioned. The cluster Colabat, containing 4 projects working in battery development, is Helios, Albatros, Liberty, and Marble. So much for the introduction, and I would hand over to Valerius. You show the slides on your own, or Sandor is showing the slides, so
Yeah.
please share it from your side. We recognize
Yeah.
that the videos are running a bit smoother if you do it this way.
Yeah, I will.
So it's your turn.
I will share
Thank you,
them.
Christian.
We
Okay.
see the slides. Looks
So
good.
everything that we are showing now is has a perspective of the thermal or the battery system, the battery cooling system. And I would like to start to give you a brief introduction about the objectives, not for the overall project, but especially for the battery cooling. We had a lot of objectives, starting with the first one is to get a technical readiness level about 7 to 8, so to have a demonstrator which is capable to let the battery operate in a certain and required conditions. With from our side and the focus, as the name already says, this is a highly integrated system, which means that we are trying to use materials or components and give them 2 functions. In this case, Sandor will show later, this means that we use structures aluminum profiles for mechanical aspects to carry the battery and to provide stiffness of the system, and also to use it for cooling application. The next focus was to reduce the overall weight. The requirement for the thermal management was just to reduce it by 1%, but to have this high integration, it also benefits, of course, on the weight for the thermal management system. So there was also a possibility to reduce it. The next one was to increase useful battery life. This is very crucial. Also, the requirements for the thermal management system means that we need a very close observation of the battery temperature characteristics, ideally in every spot of the battery system, in every cell, and to smartly provide a homogeneous system, and also to guarantee that all the cells are operating in a in their ideal temperature ranges. The next one was to bear in mind second life usage of the cooling system also, or what this means, the cooling system is not meant to be used for second life, but we need to apply for assembling and disassembling of the cooling system to be able to remove the battery or the cells, to give them the chance to quickly integrate them to other systems for other applications. The next one was to make it like to develop solutions adaptable to any kind of cells, to have a highly scalable systems, battery system, to be able to capture any kind of dimensions and requirements for different kind of systems, to have also a modular platform within a subsystem. The next one was to reduce the charging, or to implement fast charging or ultra fast charging into the battery system. You have to bear in mind here that it's always very relevant what kind of battery are you using, and what is the allowed what are the allowed C rates that are feasible to be charged or to be used for charging or discharging. In this case, as Christian mentioned, we had the CALP cell with NMC chemistry and 85 ampere hours. And as you see here, this is the final outcome. We had two different demonstrator battery cells. One is the 800 volt system, and the other one is a 400 volt system. And the bigger one has 32 modules with 12 cells per module. And as you already maybe recognize, we achieved the fast charging capability due to the cell limit by using a flexible voltage level and to use 800 volts for charging. The last objective or requirement was more from control, so we need a precise temperature management positions to be able to smartly control the battery cooling, and this was achieved by new sensors and a smart sensor position between the cells, which will be shown later. Shandon, next slide, please. Due to the change of cells, we really started from scratch, and there was a feasibility study, more details later. But we started from scratch, and we also investigated different kinds of coolings to really properly design a system which is custom made just for, in this case, for this CALP cell. And this led us to two-sided cooling. There is the bottom cooling and the top cooling. And we were focusing more or less on these requirements, which we set up to have a maximum exhaust heat of 10 kilowatts at a cooling temperature of 60 degrees. We had a heat up time of 15 minutes from 35 C to 60 C. A cool down, also same temperature level from 0 C to 35, also for 15 minutes. And to have also a limit in the pressure drop of the overall pressure system to also decrease the energy consumption of the pumps in the system. Very important, especially for battery health, is to achieve at least the limits and the ranges for the spread within the cell, the temperature spread within the module, and also in the pack, which are mostly relevant also for battery health and lifespan. We had some requirements that we created on the thermal resistance in between the systems from cell to cooling system and also to ambience. We had also to apply for the costs to generate very flexible and cheap systems, also using not standardized but custom-made aluminum profiles, also to carrying for heat piping to bring in the coolant to the position where it's required for cooling. And also in the same manner, like weight reduction was not really the major focus for the thermal management system but for the battery system, and to apply for recycling and materials, also to have a focus on materials which are not hazard to the environment, for example. This can be very critical for thermal paste and thermal gap material. And also to have a view and to bear in mind aspects from manufacturing side of view, to have it quickly and in cheap production for this recycled aluminum, which was also used for the cooling piping. Shando, next slide, please. What were our expectations and maybe also challenges from this side? There was for the temperature homogeneity there and scalability bears some kind of challenges there. Sometimes there is the positioning of the battery gives us a possibility to have a mostly efficient usage of the space which is available, so you can put more batteries into the system, which is still fitting underneath the vehicle, but you get some challenges and problems from the thermal system side to have a mostly homogeneous cooling, to find arrangement of the battery modules to really apply for most effective usage of the space, and also to have a very homogeneous temperature distribution, to apply for fast charging, which is also related to the maximum performance of the thermal and HVAC system. In this case, because we switched it to a 800 volt charging procedure, it was from thermal management system, it was not challenging. This is also why like immersion cooling was not really required, and the maximum C rates for the cell, they were limited by less than 2 C. This was, to be honest, it was not very challenging from the thermal and HVAC performance side for the battery cooling. But the other aspects were definitely challenging, especially also the industrialization aspects. And we had the idea to also use the recycled aluminum profiles, as you can see in the right upper corner, and to have these profiles which can be, you can add a profile and change the dimensions of the battery system. And within this profile, there is an integrated cooling system. So the cooling, the profile is flooded with water glycol mixture for coolant water to add cooling to the battery. The environmental aspects, so to use environmental friendly aspects also were challenging, because a lot of materials which are very attractive from thermal aspects are not really environmental friendly. So it took us a while to find materials which have good good performance from thermal side and also apply for an environment. Another point was the scalability and industrialization. You could put it together to have a way of like modularity to be able to apply for scalability. And this is just a small example of these two different types that we currently build up, a 16 module and a 32 module version. And also to make just a very small deep dive on the foam part, which Christian already mentioned, just to give you an idea what was our trial to do. Christian and his department, they are able to create foam structures which can also change locally the structure size of the foam, which relates to different kind of maybe, for example, velocities of the fluid locally. Yeah, and you can more or less, you can control the orientation of the foam structure, and you can also manipulate within the foam, manipulate the characteristics of cooling demands. And in this case, it was planned to integrate foam into this aluminum profiles, which are used as cooling channels, and to homogenize the flow distribution, and also to increase the efficiency of cooling at the transition, which not worked out. And additionally to that, it was also to plan to introduce foam structures between the cells due to limited space and not required really thermal performance. This was not realized at the end, but it's still very interesting technology, just to bear in mind. If you combine it with lightweight overall battery system structures, and you have the possibility to also integrate a mechanical stiffness for concepts for cell to vehicle architectures, and you will be able to provide stiffness and cooling at the same time, combined with a lightweight concept. All right. Now I'm forwarding to Sandor, and Sandor will introduce in a very deep detail the final outcome and the desired thermal battery cooling system. Thank you.
Thank you, Valerius. So
Thank you.
I don't know, do we want to mention about if you want to ask questions, just put it on the chat, and then we will have a look after the presentation.
Yeah, I was just about talking about that. Yeah, just place it in the chat and we will have a discussion on the very end of the presentations. And you are more than welcome to ask all your questions. And there are some questions probably on the electrical side, which might be so detailed that we are not able to answer all of them. And in this case, I strongly invite you again to the final event presentation next week. But Sándor, now introduction of the cooling system.
Yeah, thank you. So after this extensive explanation of the challenges and problematics of the project, now I'm going to show you the cooling system. And that is our, let's say, black box, which we want to, conditional as a thermally conditioned well. So this is our scope. Explaining now the setup of the cooling. So we have the cell. We have then terminals on that cell, which are the only thing which is welded in this module. They are welded to the terminals, and but it also allows us to have this bolted and flexible bus bars then, and it has to be also flexible because of the tolerances of the due to the manufacturing. So we have flexible and bolted bus bars on that, and then we at the end decided to using an aluminum cooling fin, which then responsible for the homogenization of the temperature of the cell. And this one has to be, of course, thermally connected to the cell. That's why we are using thermal pads, which are easy to remove and easy to apply. So all these aspects, easy to assemble and disassemble, are considered during this, development process. And as a last part of the cell unit, we have a compression pad, which then also, of course, accounts for the swelling. And additionally, it might slow down thermal propagation in case of thermal hazard. And this small video shows the sequence, how is it assembled. And on the next slide, I can go to the module level, also a bit animated. So the module consists of 12 cells, and then we apply a bottom profile, as it was already mentioned, which is then filled with the coolant. And of course, there is a thermal pad, which then provides us the connection. And for we have also a top cooling rail, which is responsible to eliminating the hotspots due to the bus bars, because during cycling or during fast charging, you can have quite hot bus bars on the top of the module, which then, on the other hand, introduce again temperature inhomogeneity for the cell. And this one, we wanted to eliminate that. And in order to do that, we have a top cooling rail connected with thermal pads. And in this picture, you can also see our, or at least a CAD, a picture of the flexible bus bars, which then bolted to the cells. So this is our module, let's say. And as the next level, we have PEC. I'm showing now the 8, so the big one with the 32 modules. So we have then practically 8 rows with 4 modules, and we have a cooling distributor on one side of the PEC, which is also very simple made because it's just a very simple piping. We have to ensure, of course, the flow distribution, that it is even in each parallel low. So we introduced some throttles in the piping, which was developed with the help of simulation and later on checked with we did some physical testing in order to check those diameters what we derived. So in that way we ensure that each parallel row have a same flow, volume flow, and the only let's say temperature difference what we got here is is due to the fact that the modules are serial. So the module on the rear is seeing a higher temperature of the coolant, but we checked this on the simulation, and I will show it on later. We are still below our targets with regarding temperature differences, and yeah, as you can see, also I'm mentioning here again, the cooling system is very easily adaptable to different sizes. In this project, we had 2 pack size, and yeah, it's quite easy to adapt it to a shorter battery pack, let's say with 16 modules as well. The cooling system is also capable of cooling the power electronics, as you can see on the rear side of the pack, including the junction box, which is responsible for the switching between 800 and 400 with the big pack. Sorry. For the cooling development, I'm showing now the position of the throttles and the volume flow distribution, which we determined with the help of simulation tools. So you can see here the positioning of the throttles inside the system, and this development also was a part of the project. In the next section, I'm going to explain how we developed this, and now I'm trying just to summarize it for this part. Okay, now I'm going to explain a little bit the intersection between hardware and software, because also in this project we are developing a battery thermal management system. This is a control logic responsible for the cooling and the strategy. But for that we need, of course, thermal sensors, and we position them in a smart way, because we did the simulations, and of course we have seen where is the hotspot of the cell during fast charging or charging cycle, and we equipped the module with many thermocouples. Every cell has a thermocouple, and this information is then provided to the BMS, and then at the end the BMS provides this to the BTMS, so we can we can develop our strategy for the cooling based on those information. Okay, another let's say a very simple explanation of our BTMS strategy. So we have the hardware on the left hand side, we have the BMS, and so the BMS at the end provides information about the current, actual current, and the temperature vector, let's say, to the BTMS, and some other information which is not listed here, but I have a slide to that in this presentation. So all this information then is let's say processed in the BTMS, and the BTMS then provides a target volume flow and a target inlet temperature for the coolant, which should come into the cooling package. In this in this project, we don't have a vehicle, so we were planning this to do it with a conditioning unit in a test bench. So that's is also mentioned here, and this conditioning unit then can provide whatever temperature and volume flow, and this is also an information for the BTMS. So this kind of hysteresis can be considered. I wanted to mention here as well that for the BTMS, we integrated a kind of digital twinning. So based on the sensors, but actually less sensor would be also enough. We can provide a minimum and maximum temperature locally on the cell, and of course also the middle temperature in a fast running manner. So this digital twin can run on a very simple on the hardware itself, so it doesn't need a high computational effort. And but on the other hand, the BTMS is just a state machine based algorithm, so not let's say state of the art, and also capable of preconditioning. But in this project, we didn't have the possibility to develop preconditioning models. It's just the BTMS has accordingly a different approach if we know that we are in a preconditioning state. But that information, when we are in preconditioning, it would be a scope of a different project. So with that, I can try to summarize at least the definition of the cooling system layout. So the achievements, what we try to reach, at least from the previous previously explained challenges and requirements and targets of the project. So we have a cooling system which then has a good temperature homogeneity. I will show it then on the second part. The thermal resistance is also close to the target. We were successfully implemented the cooling system, which is easy to assemble and disassemble using bolted connections for the bus bars. It's very simple piping. It has a modular approach, which was previously defined. The system is scalable as well for bigger and smaller packs. We have smartly placed sensors as well as a control algorithm for the thermal management system, which is also capable of digital twinning and also preconditioning if it's needed. So with this, I'm done with the description of the cooling system layout. If you have questions, you can then just write it on the chat. We will answer it later. But my presentation will be complete with the second part. So I'm going to continue, if you don't mind.
Yeah, just a short comment from my side. All the audience, just a comment so far that we are a bit ahead of schedule. The reason is mainly that the original intention was to have the whole workshop in person. And usually there are more disturbances and more questions right away during the presentations. And so they usually take a bit longer. And online we are a bit faster. So we will have more time in the end. And also there was already some comment in the beginning. We will probably skip the coffee break that was planned. And this way we should finish quite early compared to the schedule. So Sandor, it would be interesting to see the next step.
And all of you will be able to join the lunch break earlier. Yeah. So
I know that the first presentation was planned to have 50 minutes, but it was a little bit quicker. But now the second part is longer. So yeah.
All right.
I think I will fill the time.
I'm curious.
Okay, so as I mentioned, I wanted to explain in this section how we developed the thermal management system. So it was basically mostly a virtual development system, development process, which consists of, let's say, these 5 parts, but you can, of course, there were some different steps as well. Well, I'm trying to just summarize it like this. So at the first task, I call it like thermal system layout definition. It's a kind of pre-concept study where we evaluate different cooling concepts. We evaluate if, in a thermal perspective, what are the if they fulfill the requirements of the temperature of the temperature homogeneity, the thermal resistances, and so on. And this one, yeah, I have some slides to this as well. This is the first step, and then we came out a kind of first concept, which can be immersion cooling, bottom cooling, whatever, state-of-the-art cooling, or some wild ideas as well. But yeah, let's say this is the first step, and then I call it cooling system design, which then considers the complete battery pack or the complete solution, and where we also consider already the cooling flow or the piping, in this case the pressure drop as well. The flow distribution is also an integral part of this development process. But this is also an iterative process. It's not always just like 1 and 2 and so on. We also in this project, as I was already explained before, had some challenges due to, let's say, change of a battery cell. So we already performed the first step with the preconditioning or the pre-concept study. We came out with a concept, and we were just developing the cooling system design when came out that we have to redesign the thing because the battery cell is, for example, changed. So, but with this approach, we could easily adapt again the concept study to the new cells, and then practically we did a new iteration loop with the adapted cell with the new cell, and we adapted the cooling system accordingly. That also had some consequences, as Christian mentioned. Some of the techniques what we wanted to use went out because of weight and cost and so on. So that that concludes, let's say, this development of the cooling layout, and then it has to. The next step is as a performance check, which we did with a high fidelity 3D CFD simulation. But of course, this is based on some kind of. In this step, we did it with a kind of stationary approach, where we had some. We have to have some assumptions, of course, at this point still, and we tried to, let's say, assess the system regarding the temperature again, but very accurately, the heat flow situation, heat transfer coefficient in the cooling channels, thermal resistances, and so on. So with that, let's say, performance check, then we also went to the development of the battery thermal management control algorithm, where we also had to consider, of course, all the requirements again: cooling up time, heat down, actually heat up and cooling down. Sorry, and all these requirements has to be captured, and the strategies what we wanted to use if we want to, let's say, extend the lifetime of the battery versus if we want to allow fast charging. So all these things has to be considered in the strategy, and that's the development, and that goes also parallel with another high fidelity simulation, where we again consider the complete pack. We integrate the BTMS into the simulation, 3D simulation, and with that kind of performing a series of 3D simulations of different driving cycles. With that manner, we could just improve our BTMS by this, what I mentioned, is digital twinning, where we can then, on the fly have the minimum, maximum temperature of the battery, and that information is there in the quick control algorithm. And what is not mentioned here, but it's also was an integral part of this development process, that we had some validation studies as well during the different phases. And that allows us to, let's say, trust to improve trust into our simulation models. And then at the latest phase of this project now, which is actually now, we're going to have extended validation with EVIL tests, and different partners are performing tests with the cooling system, checking the impact of cooling on life cycle and of the all these aspects. So sorry. Now I'm talking about the layer definition phase, the first small rectangle. As I said, we were considering different concepts and studying it in more detail. As you can see on the right-hand side, there's a small summary of different cooling concepts. It's not everything included here, but let's say this is what we investigated more or less. So immersion cooling, liquid cooling, we had some state-of-the-art where the cooling plate on the bottom or between the cells with some aluminum fins connected to the bottom, or we have top and bottom cooling as well. We tried out here different techniques. We also wanted to use at this phase some kind of heat pipe technology, which then, let's say, between the cells, applied between the cells. And with the heat pipe, you can have a very good heat conduction in a certain temperature range, which would be very, very good for the thermal system. But during the development process, due to different challenges, of course, some very good techniques can fall out because of the price, because of the environmental friendliness and other aspects. So this is actually was the case for that. And so the green ones, I'm going to show it in more details, but what I also want to mention here, that instead of building these concepts in a 0D, 1D approach with thermal networks, we used a 3D approach, which is a coarse one. So we let's say build up a 3D model of somehow always a similar manner, but different cooling techniques. And we did those comparison with a coarse 3D simulation, which runs also in a couple of minutes. So it's not very time consuming, but it gives you more detail about the environmental impact. You can have also fast charging. You can have steady and unsteady transient cycles. So you can have a very good assessment of the different concepts already in that level using coarse 3D simulations. And this is something what I think is it's quite unique in this project, that we didn't use here thermal network modeling. We were using it in a 3D manner already in this phase. But of course, there are in this time point, we have a lot of assumptions, and that's the danger. If you don't have the good assumptions, you can have some misjudging of the different cooling concepts. Sorry. Okay, this is just a video. Okay, we can just skip quickly. So this is a kind of summary of the results from the thermal perspective of different concepts. As you can see, we have fluid cooling, immersion cooling here compared, and I have it here, the local cell temperature differences, and also in the module based on average temperatures of the cell, the thermal resistance, where I took as a state-of-the-art bottom cooling as a 100%. This is normally something like 1 and 1.5 Kelvin per watt, and you can see the differences due to that. So, of course, from the thermal perspective, immersion cooling would be the best one, because this is the perfect, let's say, provides you the best thermal resistance and also the most homogenic temperature distribution. So this would be very good, but this, yeah, that would be very expensive. That would be, yeah, problematic from many aspects. So at the end, let's say, you can see we have already quite good solution with aluminum fins between the cells, and that's is a good, let's say, introduction to the next slide, where I'm trying to sorry. The decision matrix, what we used to decide which cooling concept we are going to see as a final after that. Here we consider not only the thermal aspects, but also some pressure loss, other aspects like thermal hazard, maintenance effort, weight, and many different, which are also very important for the final concept. And that at the end, and of course, the cost is very important. So then we came out, and for the project, it's actually sufficient and enough to have a cooling system with an aluminum fins between the cells. So this is our and that way we decided to go on with that design. And this is I think the process how we came out with this cooling concept, what I shown in the previous section. But of course, the next step is, as I said, is an iterative process. But we also, let's say, consider the complete pack. The flow distribution has to be considered, because as you, from cell level to module level and then to the pack level, you have, you have to also develop the corresponding parts. And so we did it in a very simple manner, because we have some different diameters for the different rows introduced and the cooling distributor, which then at the end results in a quite, let's say, even flow distribution. And also the pressure loss is fulfilling our targets or requirements. So we are practically, in this very simple manner, we then, as I said, we can ensure that the temperature homogeneity and the pack is okay. And for that, for example, I just mentioned here on the bottom that we developed, for example, like an automatic joint-based method to derive these diameters. This is also an interesting method what we tried out in this project, and was successful method to find those diameters instead of manual try and error method. Okay, then I'm going to switch now to the performance check. That was more or less the third rectangle on the process. So this is again, let's say, a very detailed 3D simulation with fluid and solid considered, and but it's still based on the and some assumptions. But we tried to, let's say, use here a load case or a case which then represents a kind of worst case. So we have a heat rejection in the cell, which is Yeah, and at this phase, maybe we have already some information from cell characterization. We can have some kind of assumption about what is the rejected heat in the cell, and we just took something like a middle value during fast charging, this which is about 10 watt. And we also consider in this case ohmic heating of the bus bars, and in the simulation tool you can model it, including thermal resistances due to the bolted connections and electrical resistances as well. So all these things then provides you, or gives you a very accurate representation of the temperature field. And the results are shown here. So at the end we got, for example, for one row, what you can see, one row of the cooling system. So we have a temperature difference in the cells, all in all, locally below 5 Kelvin, which is quite good. I mean, our target was 10, so we are way below. The average, considering the average temperatures, we are also quite homogeneous. The only thing which is maybe a little bit less good is the thermal resistance to the coolant from the cell middle, but this is actually a quite good value still, considering the state-of-the-art batteries. So we were satisfied with this, and then we go to the next rectangle, which is the development of the BTMS. So as I mentioned here, or the previous presentation, we have some inputs from the battery. Let's say through the BMS, we got temperature vectors, electricity, and so on. And here I made a complete list of the input signals and the output signals of our BTMS. As you can see, I'm not going to explain all of that, but I just want to mention here that we have many different let's say variables which define the state of the battery. We have they are using the coolant inlet temperature, the actual coolant inlet temperature also as an inlet. This accounts for the hysteresis due to the conditioning unit, or in case of vehicle, that would be also the case, that your thermal management system not always provides exactly what you want. And on the right hand side, of course, you have the target volume flow and also the target temperature, and we have also a heating request for in case of heating up the battery. So this is the input and output description of the BTMS, let's say, at this, and this one of course enables a safe and more or less effective operation. As I said, the last rectangle on that development process was this one, with a high fidelity simulation with performance check. So this is let's say a complex back simulation with sorry, with a cell model which is based on some electrochemical model. We integrated this to our simulation tool with the help of FMUs. So FMU is it's a workaround to do co-simulations between different systems. So our 3D simulation can communicate in that way with a P2D electrochemical cell model. We did the same with the BTMS, as you have seen before, that our BTMS can be also exported as an FMU, and then it's also let's say in the simulation it's easy to implement everything and put it together, and then we can have a complete simulation. And
I think, maybe let me add one information. So it's of advantage that we are able also to use control functions from 1D model, the BMS function, and can integrate into our overall simulation. Yeah, so it's also possible to take virtual sensors from the 3D CFD simulation and use this information for the 1D FMU model to also apply for derating, for example?
Yes, I wanted to explain the next slide as well, how we used this kind of simulation to improve our BTMS, because it was a part. We used this high fidelity simulation in order to train our very simple model, which then provides us the temperatures in different locations, and also locally minimum maximum is possible to define. So as an example, you can see a driving cycle on the left-hand side, which consists of intensive driving and some charging. So you start with a full battery, you drive it empty on the highway, and then you just let's say charge it again. And for that, what we did is we took only one sensor of the complete module, and we can have then we can train the model, and it is able to provide us, for example, a temperature value on the bottom of the cells. As you can see here, this BP code 3. This is a sensor which is placed on the bottom of the cells, just below the cooling. This is one of the coldest position of the cell, and on the right hand side you can see the straight line is the simulated from the 3D. That is the value from the 3D model, and the dotted line is from the fast running model, and they are quite well capturing each other. Or the agreement is quite good. The same applies for the middle temperature. So we can actually, with this methodic, we can just reduce the number of sensors if we want. For this Marble project, we had quite good amount of sensors there. So, for example, average to predict the average temperature of the battery is not even necessary, because we have that values as a vector. But if you want to know what is the actual minimum temperature in the battery, then it's good to have such kind of virtual sensors. And this one we did with the series of 3D simulation. But of course, this can be done also with testing. And this, with this method, which is demonstrated that this can be done with the simulation as well. And maybe in a later phase of the project, if we still find the time, we can even check this against some measurements. Okay, another slide again, just very quickly, is about the local maximum, local minimum temperatures, which I try to explain here. So on the right top figure, you see, for example, the temperature differences. So the black, concentrate on the black line, please. That is the temperature differences during that driving cycle, based on the sensors which are physically there in the system. So you can see that the maximum temperature difference, what we see there, is about 2 Kelvin. The red line is this from the simulation, the 3D simulation. This is a local maximum minus local minimum for the complete battery module. And that is almost like 5 Kelvin. So that's significantly higher. So this information is required for the BTMS because it can change, it has an impact on the cooling strategy. So that's why it's important to include an accurate information about the local temperature difference. So, and so I just wanted to explain that even if you have a smart placed sensors, it's not always capturing minimum and maximum the complete temperature difference in the cells. In order to have a precise thermal management, you need to do that. And what we did as well with this fast running model, that we trained the model, and now it is not very good agreement, but at least it provides you a way better temperature difference than what you got from the physical sensors. And the reason for this not very good agreement is that the position of maximum and minimum might change during the cycle. So sometimes when you have a fast charging, or you get a hotspot in the cell middle, let's say, when you have operation with driving with very high let's say current, then maybe this hotspot is just another location or close to the bus bars. And this one, so this changing of location of the minimum maximum, this is not well captured with our model, but as I said, it still gives you a better approximation of the actual temperature difference happening in the battery than the one which is then provided by the sensors. Yeah, so this is more or less my presentation. The last slide is just in summary again. So we applied a virtual development, mostly the virtual development process with very few validation studies, and we tried to overcome the project challenges with more or less success. We developed also the BTMS control algorithm, which is capable of digital twinning on the fly. And as another, let's say, outcome of our project work is that we developed complex high fidelity PEC simulation, which then really allows us to develop a precise thermal management, as I mentioned in the previous slides. There are still some points which is that would be very nice to continue this project in a longer period. Let's say we need to, it should be done at some point, an extensive validation of the BTMS with the measurement results, which is just produced right now in some other institute, maybe at this very moment. And yeah, the last point what I said is also already said before. Yeah, if you want to have more information about the Marble project and battery pack in a more holistic manner, then it's strongly recommended to join our final event. So with that, I'm done.
Question concerning the immersion cooling, also the criteria for chemical compatibility to solid parts. Maybe just to add or to answer this question, during the feasibility phase, it was not possible to get any kind of information from the cell manufacturer concerning any kind of compatibilities with that kind of fluid. So the cell was not intended to be used for immersion cooling, and we couldn't get the approvals from the cell manufacturer to use immersion cooling in this case. This was one point, and the other point, at the end, we changed the cell, and it was the same with the second cell manufacturer, and the C rates, the maximum, were slightly lower than from the CATL cell. So also the demand for immersion cooling was not there anymore. Yeah. I hope this answers your question.
I hope so. Yeah.
Okay.
Otherwise, we can clarify that maybe later in the discussion. I think Rico just wrote thanks. So yeah, I think it just hasn't been necessary to have an immersion cooling. Yeah, there were easier ways to achieve the cooling that was needed.
Yeah, there was different aspects as I mentioned, or we mentioned all the dismantling, assembly, the environmental impact as well. So it's way more convenient to use just a simple aluminium profile if it's sufficient for the cooling. So that's why we at the end don't have any graphene coating. Everything is just was not let's say, from different aspects was not good enough.
Right. So I think that is your sharing, and I'm switching to the next part. I hope you can see the slide.
Mm-hmm.
And yeah, we come to the next point. As I said, we are a bit ahead of schedule, and we will skip the coffee break. I hope it's not that boring. The next lecture is not that boring that you jump over and go to the coffee break anyway. I'm talking about the industrialization of battery system from development to mass production. There are just some certain points I can show here, because I mean it's a long step, of course, and the industrialization is a point that you always look at for the future. But we are developing a new battery system, so we are not yet on industrial scale, and we are definitely aware of that as well. So we have a TRL level that is supposed to be between 6 and 7, and we will stick to that and not coming to the final version of an OEM application. So the talk is actually separated in some approaches. I want to show something about the material, the processing, and other approaches that might not have been come into the system. Starting with a slide you might remember already from the first presentation. So we started with a material approach to have a lightweight and sustainable battery housing, meaning we use post-consumer scrap and use that for aluminum production and create certain types of profiles I will show later on. And by those profiles, we have the opportunity also to scale it. You have seen already the 400 volt and the 800 volt version of it. There would be many different sizes appropriate as well. And of course, by this modularity, there's nothing glued or welded. And you heard already, we avoided in the end also the immersion cooling, because it's supposed to be repairable and also easy and safe for assembly and disassembly. All those points have been mentioned already, so I come to that a bit deeper in detail. As I said, for the material side, for the battery housing, we have used aluminum as an aluminum housing realized by extruded profiles. The material was post-consumer scrap, you see on the left, and it actually had to be collected, shredded, identified by, for instance, LIPS, and in the end molten to the first ingots. Those have been casted and remolten, chill casted to extrusion billets, and finally extruded. And in the end, of course, if you want to have a certain structure out of it, it might be deformed as well. On the very low side of the picture of the slide, you see some microstructures, and there are different contents of scrap that we used and combined with virgin material of 6063 alloy. And we started with 20% scrap and increased it step by step up to 100%. The result actually showed that we had the extrudability remained. Yeah, so it was extrudable in all the ways. And how is that actually achieved? We collected the scrap, and here you see one stress strain curve that is very close to the original size. We chill casted this material to create some billets of small size. That's about 30 millimeters in diameter, and used one of those presses to create the first extruded profiles, to do just some laboratory experiments of it. And also, in this case, we have been able to do the first tensile tests and things like this. So it was mainly laboratory scale for the analysis of the material behavior, and also to predict some parameters and prognose some parameters for the serial manufacturing. In the series manufacturing, you're dealing with much more material. And if we would have recognized in the very beginning that the scrap content is somehow not working out the right way, we could have skipped that and improve in the laboratory scale before. Yeah, coming to this large scale, sense of the whole project was a functional integration. So we actually integrated, as you have seen already, the cooling within the battery box. So those profiles we have used have not only one job to do, they actually have several. And one of them is, you see those small gaps in the actual floor of the battery housing. They're responsible for the cooling liquid. So they are actually flooded. And this way we have increased a little bit the complexity of the profile, but decreased the complexity of the overall system. And also the height of the whole battery pack has become a bit lower. Yeah, it's using this sort of extrusion for the manufacturing of those battery boxes had the advantage that we have a serial production process. And as you have seen already, and you can see it on the middle picture as well, an adaptable geometry is possible in length and width, so you can scale it to whatever size is needed. That's actually a picture, as far as I know, from the mini housing that has been produced for some analysis in laboratory scale. And then we had an original housing of 400 volt and one of 800 volts with the 32 models you have seen before. Yeah, on the very lower picture, you see the chill casting on the left side. So these are actually the billets casted out of the recycled material containing alloy. And on this middle picture is the extrusion press actually creating the side walls of the battery pack and also the floor panels. Yeah, then as we have talked already quite a lot, I'm gonna show you some video again. I hope it's working and you can actually see it. That's about the assembly. So a prototypical assembly usually is connected also with manual welding. In our case, we established an automated welding by robots. And you see that's the battery box. We have some weld beads on the side walls. And of course, we have to interconnect all the floor panels as well. This way also creating parallel the cooling of the battery cells. And you see on the very smaller picture on the lower right corner, there is a monitoring of the welding process. So it's continuously supervised, and you see actually the weld beads look very homogeneous and nice. And yeah, now the people have to speed up a bit. And sometimes you see there's a welding of only part of the weld bead of the overall length or something like that. That's the strategy of welding to avoid tensions during the assembling process. So now the inside is actually welded, and yeah, it has to be a sealed system in the end. Also in one case because of the cooling, and in the other case, of course, to protect it from environmental influences. I'm going to speed that up a bit. Again, you see the melt bath of the welding process and the supervision of that. And if you have further questions, I'm sure the colleagues and project partners from SINTEF in Norway are happy to answer your questions if you join the final presentation in the final event next week. Yeah, we have seen already some slides and videos or animations of the assembling process. And this is a process I found rather interesting as well. As for me, it was the first time as well that I have actually attended such an assembling process. And to give you an impression how it looks like, here's a video of the assembling process realized by AVL Italy. Antonio is explaining it. Is then the voice working?
No, no sound.
Ah, 1 second. I will just shortly unshare my screen and share again. So jump back a little bit. And we try it again. Now working.
No.
That's strange. It should work. So maybe is one of you able to explain a little bit about it? In the end, most of it is already shown in the pictures. So if I say anything wrong, just let me know. First of all, of course, the preparation of the cells. Here you see already the thermal pads that are adapted to the cell, the compression pads, now the sensors for the thermal parameters. And we had a question in the chat before. The material is shown. Now 6 cells are actually already assembled. You see the thermal, how do you say, guide sheets, or the transmission of them. The compression you have seen just for a short moment, and now we have the interconnection of all the electric and sensor system.
As you will maybe mention, there is no welding on module level. Yeah, so also the busbar connections are bolted or screwed, and you can quickly and easily disassemble everything. And also the module size was also designed not to be too heavy, to be liftable by people.
Yeah, you see it. I mean, it's probably made on purpose, but you see they are handling the whole module just with one finger, so it's not that heavy. All the additional parts adding to the cell are meant to be lightweight design as well, so it's taking into account that we have a low weight. And now you see the model will be assembled into the battery box. Here you have
pressure test. Tightness test. And you see the profiles, and you just drill holes and put in connections for the coolant piping.
Yeah. Now all the modules are assembled. You see already the thermal pads on there. The interconnections by bus bars are established. Then there's the cover and the placing of the junction box and controlling. Sorry that this is not working, but I have no explanation for that. And the cover on top. As you have seen, again, no welding, no gluing, only screwing and disassemblable connections. So, yeah, I told you that I would talk about a little bit about eliminated approaches as well. We have seen already the area I come from, the metal foam part. The original idea was to increase the surface of the heat transition and for the cooling process. And the intention was to use like pipings or cooling panels, which contain a liquid like a liquid flows through the panel and a surface enlargement by a metal foam. And as we talk about foams, what is it all about? Yeah, that's Mr. Kelvin. He actually was the first one who investigated this kind of porosity or cells within foamed structures. And I'm always talking about closed and open cellular foams. Yeah, the first one, the closed cellular foam, I showed shortly in the camera. That's actually a foam with a density of 0.25 gram per cubic centimeters. It's made of aluminum, and as you can see in this middle picture, it's easily swimming. We use it very often for crash performance and also for lightweight design solutions. So it's also realized in some battery housings already, mainly for those crash purposes, for the polar test or similar. And the second version has no cell walls in there. Yeah, what you see in those first pictures, the closed cellular foam contains walls, and the open cellular foam just contains ligaments. So wherever those walls originally got onto each other, if the walls are gone, just those connections are left over. And these open cellular foams, I show it in the camera again. They are permeable, so as you can see the sun through it and liquids running through it as well. And we have a large inner surface. And the intention was to use this in these cooling panels, and also there would be the possibility to use it in the profiles as well, to enlarge the surface and also to influence on a certain level the flow of the cooling liquid running through the profiles. The reason why we actually skipped it was that those foams, to get them fixed somewhere in this long profile was a bit tricky. And in the end, we recognize it's not necessary. We showed already that there were some approaches which were a lot more efficient than the demand. And this way, we actually took a decision, also on the one hand from space, and in the second hand from costs, to reduce the complexity of the system, and we eliminated the foam. Just to show you the behavior of the foam, that it is transferring heat very good. This is actually my hand on the left side, and the colleague who is trying to, I would say to burn me, but there is a plate of open cellular foam in between, made of aluminum. And you can see the flame would almost touch me. This flame has a temperature on the core of about 1,300 degrees. Yeah, and it's no time lapse or something. It's really working, that there is no heat coming through this panel, as all the heat of this gas flame is actually distributed within the structure of the open cellular foam. And
please prove it by showing your hand again.
Yeah, it's still they are unhurt. Yeah, and yeah, the colleague was very hesitating, and nervous, but it worked out well. There are some new approaches I want to show you, are based on those experience. Usually we have an investment casting of those patterns. The ones I have shown so far and you have seen in the video, they are actually made from a master pattern that is originally a polyurethane foam. And there are alternatives as well. So in general, you can have a CAD file of whatever structure you can think of. At the moment, we print it in a 3D printer in wax and use this as master pattern for a casting process. So in this case, aluminum. And as you can see, those structures, there are several. I got them here as well, showing them in the camera as well. That's a Schwarz P structure. And maybe just to prove that there are different materials possible, that's a copper structure as well. So there are many possibilities, and I would say the limit is only your imagination. And we had one approach that is quite interesting to show. I think it's quite a new one. We intended to have an individual cooling for that is adapted to the load case of the electric circuit. So you all know those thermographic pictures coming from a thermographic camera or from a simulation where you have hotspots on some of the electric components. Usually those hotspots are shown in orange or red color, and cold spots are in blue. And if you combine that with a conventional geometrical structure, creating unit cells, as you see on the right picture, you can actually have a process where the diameter of the ligaments you have in there, of the struts, is increased, or the cell size is increased. And if you look closely, you see that there are thicker ligaments wherever you have a red color on the thermographic picture. So showing that in our case, that is actually one of those profiles we have seen from the battery box. You have the inlet, which is shown very nicely in dark blue. So it's cold. It's a cold liquid coming in. Then it flows within the profile underneath the first 4 battery cells. You have the way through to the next chamber, coming back, and have the run out on the lower right. And as you can see, the first one is cooled perfectly. The last one is a lot hotter than the first one. If you see, the range of those temperatures is still within the limits. Yeah, so we have a certain limit of 5 degrees Celsius or 5 Kelvin, but this could be optimized. Yeah, and our intention was to have an automated process where you take such a picture, put this thermographic or simulation picture in a design process, just start this sort of automated process of geometry generation. And as it is shown on the lower pictures, we had a network of single cells. In this case, it's just cylindric pins of the same diameter. And by this process, you have automized enlargement of the diameter of those pins, and you will achieve, wherever there's a red color, a thicker pin, and wherever there's a cold color, you have the original small diameter of the pin. So this way, if it is an easy structure that's like those pins, it would be possible to have even just a two-part tool for that, and you can use serial applications like high-pressure die casting to create this kind of cooling structure, which is actually adapted to the load case and individually made for this application, and will assure the best possible cooling for this certain use case. This process is actually developed within the project. We have tried it in small scale, but it hasn't been realized in the project, as it was just a theoretical approach, and will be subject for further projects which are following on after the project. Yeah, and just to give you some more impressions how those structures could look like, some more pictures of casted structures, which they actually have another functionality of a mechanical kind. Here again, the comparison: on the lower side, you have the CAD file. On the upper side, you have the aluminum casted structure. And it's a cell, when you compact it by mechanical load, you have a bending of those struts. They are pre-bent in a certain direction. They react very softly. And whenever the top of this pyramid is touching one of those crosses, you have an enlargement in stiffness. Just imagine structures like a bumper of a car. It would be possible to have a soft reaction of a bumper when you have a pedestrian crossing and there's an accident happening. You would have a soft behavior of the bumper. And as soon as you are driving on the highway, you don't use the soft behavior anymore, and you have a hard behavior of the structure, consuming a lot of energy. And also on the right side, shown in this case in copper, auxetic behavior. So it's a structure that actually doesn't expand when you compact it; it decreases in size. And again, one structure realized from or developed from the cluster of programmable materials, CPM of Fraunhofer. Also in compaction, those pins touch each other and increase the stiffness of their unit cells. So as I said, the limit of those technologies is just your imagination. And what is quite interesting as well is the lower right picture. It's of course possible to have graded structures as well to optimize the heat flow in one direction and the flow of the liquid that is running through the structure that is actually consuming or taking the temperature and heat out of the system. Yeah, so much for the industrialization. Of course, that is still quite some way to go, but I hope it just plants a little seed in the back of your mind and gives you some ideas what is actually possible. And maybe you have an idea we can talk about later on. So much for that. And we reach the next point, which is the interactive activity with players of the electronic and automotive industry. Originally, it was thought to have this meeting in person, so we all would sit on one table discussing that with a coffee in our hand, but that hasn't been possible, or not that many people actually registered for the local workshop in Ingolstadt. So we have it as a chance that you can raise all the questions you have. And there might be some, I would say, initial ideas which are shown on that slide and could be explained by Valerius, if you like.
Yeah, thank you, Christian. So just allow me to give you like a small glimpse of like future battery cooling systems. As currently, it seems like the energy density will increase in future with new battery chemistry. This is a major target to extend range of vehicles, which also will have an impact of thermal management systems. Most battery chemistries have the same like comfortable temperature range, but there will be probably changes in the cooling demands. It will be sometimes more and sometimes less. There is one difference, is a solid state, which are less temperature sensitive and which probably will need less cooling demand. What we are quite sure of is everything goes virtual, so there is software. It will also be like one of the major, or is the major trend of improvement of systems, is also to have smart controls, used artificial intelligence based control strategies to apply for very strict temperature ranges and to do it most efficient from overall vehicle side, to let the vehicle learn how every single vehicle user uses the car and the battery, and also to do an optimization of every subsystem, especially on the demand and the characteristic of a single user, and not only like a multi-purpose vehicle. For this, we're currently doing a lot of digital twinning, as Sandor already mentioned, which includes also virtual sensoring, to enable a smart and intelligent, most efficient cooling with optimal ranges within the battery. You need to know the current behavior and the status of the battery and of the cell in any kind of position. And what we are currently able to do is also to have a digital twin, which allows us basically unlimited positioning of sensors, virtual sensors, which are based on algorithms. The development times, just looking to China, which is like providing currently the China tempo, is also a major point also to increase the overall development process, to be more efficient, to be quick, and to make decisions very fast and robust. This is like virtual front loading, and in future we're seeing it now. A lot of development is done in the feasibility phase on the virtual level, and this will be increased. And I think currently the results show that you can trust simulation results, and it makes it very flexible and quick. Alternative cooling systems is like micro channels cooling might be required, might be edible. Yeah, foam cooling. Just you have to see it as like a vehicle or battery system demands overall. Yeah, mechanical demands, thermal demands, electrothermal demands, and if you put everything together, you will have an overall optimum, which doesn't mean there is just an optimum for thermal management, but the system overall needs to be maximum efficient, light, and as you can see, recyclable and reusable. Also from software side, future looks like the vehicle will understand our demands and our behavior, and it will have also, or it will have an impact on the cooling system overall for prediction, preconditioning of the battery to provide the maximum performance when you enter the car and during winter, during summer times. Currently, it's not only for battery side, but it's an overall cooling system alternative refrigerant. So there is this FAS restrictions which are currently coming from regulation side, and we are looking into alternative refrigerants, as we have hopefully shown and have given you some ideas. So it's a research project and give you hints and hopefully gives you impressions and ideas for future, which way it can take also to have smart multi-usable or highly integrated functions of different components within each other. And maybe also it depends on the development process. Phase change materials, it's always a topic. Usually phase change material was not efficient. It was just too heavy to store energy or thermal energy and to release it. But in relation to improvements from technical side, maybe it will be also future technology which can be applied to thermal management systems. Not again, but to have it really to make the system more efficient. This is feel free also to talk to us. Yeah. So if you have questions, please do it now. I'm really I would be glad to answer your questions and give your ideas. Yeah, it's interactive. Use it, please.
Yeah. No one is jumping in right now. Maybe just one comment. I see in the audience also Rico Schmerler. He is a colleague of mine worked in a different project where I have been actually working on PCM infiltrated into a metal foam structure. There are some advantages you will probably see when you enter his name, for instance, in LinkedIn. There are more possibilities of the cooling, of course, and we have seen already many approaches, and we recognized that with the project we have already mentioned, some of them, I would say, neighbor projects to Marble are Albatros, Helios, and Liberty. All four of us are interconnected in the overall cluster Collarbuts. So the intention was to exchange some information and avoid double work. In the end, it was a nice platform to discuss some, I would say, similarities, and especially in testing. It was quite difficult about the CAD design because there were some confidential information, especially from the battery manufacturers. But the collaboration worked quite well, and it will go on even after the projects finish, as we found 2 new projects jumping into the ColorPod cluster. And just to give you an impression about the thermal behavior, that there are some differences. All 4 projects had different approaches how to realize the thermal management or the cooling of the battery. The first one of them was immersion cooling. The second one was with a small bit of immersion cooling with spray cooling. Then we had a conventional, I would say, cooling pad underneath and in between, and our system with an integration of the cooling within the housing, combining the components and increasing the flexibility of the system and decreasing the size, and this way also the weight. There is a question of
Christian, maybe this is for you in terms of reusability in a different application than mobility. Let's say stationary application. What will be the amount of components that could be reused without any kind of refurbishment?
Actually, as we have strategies included, which are meant already in the design phase to take the disassembling into account, we can actually break the whole system down to cell level and can, as we monitor each cell in the thermal behavior and electric behavior, we can actually, or we know about the health of the cells, so we can use the cells again for different applications if they are still healthy. And also most of the equipment you need, except the cells or all the peripheral equipment like the bus bars and things like this, could be used for second use or I would say alternative usage as well.
This is also from the European Union and from legislation side. The battery passport and some lot activities are treating the industry also to keep in mind the all value chain, and there is a major part is really the second life, and you have to bear in mind that for a battery electrical vehicle, you need, it's a high dynamic systems, you need very high energy density to achieve the ranges. This is important for the first life. For the second life, stationary applications, the weight and the space is not that important as it is for a vehicle, and the cells still have capacities of 70%. Yeah? So there is a big chance also to use the second life, and the cells will be still will be possible. It will be still possible to provide performance or storage potential for another, maybe a decade, but a little bit less. Yeah.
Yeah, and one further comment from my side to that. I mentioned already many times the final event that will happen next week. There's another event. I'm not quite sure if it's possible that you see it right now. Probably is. You see the mail I'm showing?
Yes.
There's an event 1 week after on the 25th of March, and that is actually working on the sustainability, so circular economy and eco-design. And it will be also from the Marble projects, talking about battery life cycle assessment, cost analysis, and so on. And they actually, when you look in the agenda, you will have environmental aspects, eco-design. So if you have closer questions, especially to the matter in that you mentioned, Carmen, it would be good if you would be able to attend this sort of workshop or the webinar. They will explain a lot more about those questions. Any further questions? You're most welcome. Jump in. Tends to be very quiet. Everyone is hungry already. As I can't see any hands raised, I would say we're gonna close on that place. Having final remarks, there is not much to say then except thank you for attending. Again, the offer that we meet again in the final event presentation next week or in the workshop the week after. The project will actually end on the end of March. And if you follow us on LinkedIn or all the other social media platforms, you will get all the information about the events again. And this invitation still stands. And if there are no further questions, I thank you for your attendance. And it was great to have you here. And we will share the recorded presentations later on to all participants. Thanks a lot, and I hope to see you soon. Bye-bye.
Thank you.
Goodbye, everyone. Thank you for your participation.
Bye-bye.